So the main idea in the variational autoencoder was a kind of change in the way that we look at the generator. So what is the key difference of this generator as compared to the one we have in GAN? What is the key difference of this guy, this generator here, as compared to the one that we use in adversarial networks? So how different this guy generates the sample? Yeah, just go ahead, no worries. What is it? Yeah, it uses latent, yeah. It uses latent, that is right, but GAN also uses latent, right? So you start from a latent, you pass it through a network, you get the output, that is the generated one, right? But what is the difference between this process? So how do we do it in GAN? So latent goes inside a neural network, and then the output of that neural network is exactly your sample, right? But how do we do it in this way, in this new approach? When we pass this X through the neural network, the thing that we get at the output, is it the sample? No, it is not the sample, right? We just pass it through one Gaussian distribution, right? So we treat it as the mean value of a Gaussian, and then we sample that Gaussian distribution. That is going to be the sample output, right? So the key difference was that now we're talking about probabilistic generator, right? Whereas in GAN, we actually use a deterministic generator, right? So the generator looks at the latent sample and generates exactly the sample, whereas here you're not doing this, right? You're computing the mean value and then you use the sample at the output. So the main idea here in variational autoencoding is that we get the sample in the Gaussian space, usually, and then we pass it through one network. It's going to give us some, we called it a statistic, right? But for us, it's essentially the mean value of a Gaussian distribution. Then we have a Gaussian distribution with a fixed mean variance and mean value mu. Now we are sampling X from it. So this is an easy thing to sample. We're going to sample. This is the data sample that we have, right? So the data sample is coming out of the Gaussian distribution with the mean value computed based on the latent. This was the idea. It's important to pay attention. The key difference here is that we have now a probabilistic generator, whereas in the GAN case, we have a deterministic generator, right? So this is the first thing. And we could look at the end-to-end model as a kind of, conditional distribution, which is able to sample from the data distribution given the particular latent, right? This conditional distribution is Gaussian, right? But we talked about this fact that even though this guy is Gaussian, the data distribution is not assumed to be Gaussian, right? So what was the data distribution? What did we call it? So the conditional distribution of the data given latent is Gaussian, right? P of x given z is Gaussian. What is the data distribution? Mixture of Gaussians, right? Mixture of Gaussians, because you're going to multiply this guy to the prior distribution of z, then you marginalize it, and then you're going to get now your distribution. We talked about this, that distribution is not anymore a Gaussian distribution. This is what we call it mixture of Gaussians, Gaussian mixture distribution. And Gaussian mixture could be very general, right? So it could pretty much present any distribution that you have. This is why this thing altogether is not working fine, right? Because your output distribution, even though this is conditionally Gaussian for every single sample of the latent space, it's not Gaussian marginally. And this is what we want, right? We want to have marginally a very general distribution. So do you remember what we did last time? Everybody's cool? So that was the idea. And then if you want to sample from this guy, it is quite simple. So I have put now the Gaussian example because based on our last discussion, we know that we are going to work only with Gaussian guys, right? So if I want to just sample from this distribution, I'm going to do exactly the same way as we do it in GAN or we do it in the flow-based networks. But the only difference is that we're now doing it probabilistic. So I'm going to sample the latent space. And in the latent space, I'm going to consider just a zero mean unit variance distribution. That is very easy to sample. Once I sample it, so basically I sample m independent Gaussians. And now this m independent Gaussian is going to be my latent sample. I'm going to pass it through the neural network that I have, right? This neural network is going to compute for me the mean value of my Gaussian process. And now, out of that, I am going to sample one Gaussian sample with mean mu and variance 1, right? Now, can you tell me if you want to do it on your computer, if you want to sample this distribution, how can you do this? So I give you the mean value. I computed the mean value by the neural network. I give you that value. How do you sample a Gaussian with this mean and variance 1? Exactly, right? So you end up again sampling one zero mean unit variance Gaussian, right? So if you want to do it, essentially you sample one epsilon, and that epsilon is again zero mean unit variance, right? And then you add it up to that mu value, right? So this is like a tiny bit of noise added up around the mean value, right? And that mean value plus epsilon, this all together is again a Gaussian with mean mu and variance 1, right? So this is the way that you generate it on your computer, right? And now you see that this is very easy to sample on your computer, right? Because Gaussian, ID Gaussian is a simple thing to generate, and you can, of course, generate X accordingly, right? Everybody's cool? Questions? Everybody can remember? Cool, great. So one thing that I'm going to do today a lot is this N0 here. And when I show N0, I simply mean zero mean unit variance, okay? So this is the easy guy that you can always sample on your computer. Okay? Cool. Now, this is sampling, and we wanted to train this architecture, meaning that we wanted to make this maximize the likelihood given the data that we have, right? And the problem that we ended up with was the kind of challenging problem of computing the marginalization of the model, right? So let me just reformulate it for you once again. So I want to do maximum likelihood estimation based on this data set that I have. Every single guy inside this data set is a data sample coming from data distribution. What I want to do, I want to just maximize the likelihood, right? So the likelihood of the model, so it depends on theta, and theta is all the parameters inside the generator, right? Which is essentially the parameters of the neural network computing the mean value for me, right? Just look at this slide once again. Keep it in mind. This guy is the only guy being parameterized here, right? So this is the neural network. Getting one number at the output give me another number, right? Getting one vector at the output is another vector. So this guy is the neural network, and theta are the parameters. Here, anything else is quite fixed, right? So there is nothing to tune there. So now I want to compute the likelihood for this particular model, and the likelihood is going to be the product of the all probabilities on the data set, or it's better that we work with the log likelihood, so it's going to be average of the log sample likelihoods, right? Great. So sample log likelihood is essentially the marginal distribution of my data, or my model, sorry, at the point xj, and then I average them over everybody, right? So we had it before. I'm going to represent it with this notation. Everybody's cool with this notation, right? So instead of summation over those samples, I'm going to say that this is estimation of the expectation over the data distribution of this sample log likelihood, right? And what I want to do, I want to maximize this guy, right? But this particular distribution, this is the marginalized version of the model distribution. And I don't have the marginalized itself, I have the joint distribution, right? Because I have the p theta x given z. This is the Gaussian distribution that I built with my generator. I have my prior distribution of the latent, pz. If I multiply them, I have the joint distribution. That is easy. But I want the marginalized one, which means that I need to integrate it over z. And we talked about this. This is a challenging thing, right? And to resolve this issue, what did we do? We just developed the evidence lower bound, right? The whole variational inference framework, right? So instead of, if you want to compute the log likelihood, which is called log evidence in that framework, if you want to do that, just go ahead and compute the evidence lower bound, which is now feasible for you to compute, or estimate at least, and then you try to maximize it over all modeled posterior distribution that you have. This maximized version is going to be either the likelihood itself or very close to that, right? So it was a very tight bound. So instead of solving this problem or computing this integral, we're going to just go ahead with the evidence lower bound, right? Everybody's cool? Good. So that is the maximum likelihood training if you want to do in this new architecture. Basically, we are going to use ELBO, and ELBO, I mean, is something that we can compute if we just do one particular modeling. So if you consider one conditional modeling here, which is the model for the posterior distribution, we talked about this before. That is the distribution which is good, giving us good samples for a given x of the latent space. So if we can do if we have such a model, then we can replace it inside the evidence lower bound, and then we can compute that evidence lower bound for this particular model. Then we try to maximize it over all possible distributions, right? So we consider a class of distributions. We maximize it over that class of distribution. This particular term is either exactly the log likelihood that we want, or it is very close to that. It's a very good approximation of that, right? And then we want to maximize log likelihood, so we're going to maximize this other term, which we now can compute, right? So purpose of variational inference framework. Okay. Now, one thing that you might ask me here is that why I put here in the index theta and xj, right? So when we talked about the variational inference framework, we thought of the data distribution being fixed, the model being fixed, the latent distribution being fixed, the model being fixed, and also we talked about only one single sample, right? Now, let me just write it down again, write the ELBO again for you, because we're going to play with it quite a lot today. So this is the ELBO, right? So this term is the model, right? This is the Gaussian term that we have. Now, in the original framework, this was fixed. Now, we consider this guy to be parameterized by some theta, right? Some neural network, right? So this term is, of course, depending on that theta as well, right? Obvious. Another thing is that this is given for one particular x. If you remember, we are doing all the averaging here on z, on the latent, right? So x is fixed, right? So for every single x, you are going to have one separate ELBO, right? You have multiple samples. Every single of them has one likelihood, right? And for every single of them, you have one evidence lower bound, right? You need to maximize that evidence lower bound to get the likelihood of that particular sample, and then you can do maximum likelihood. Everybody's clear? So don't get confused. I mean, I put this in purpose here because I want to make it clear for you that it's not only depending on the model you consider for your distribution. It's not a kind of universal bound for every single likelihood that you have. It depends on the point that you're working on, right? On the particular sample that you're working on. And you can guess this is going to add extra computation, and you are totally right. We're going to see this, okay? So at the end of the day, you have this particular term, which is depending on x and theta, both of them, right? And because of that, this ELBO is depending on both of them, right? This other term here is not really depending on those guys, right? It's going to be always fixed because it only depends on the model you consider for Q distribution and the prior distribution of the latent, right? Which is fixed regardless of the sample that you're working on or the generator that you're considering, right? Everybody's cool? Okay, so now what we want to do, if I have one particular point xj, I look at this guy, I put xj here, I put the theta that I have here, so they are going to be fixed. Now I want to maximize this term over w. If I do that, then I'm going to get likelihood, right? And I need to do it for every single point so that I can compute the objective function of maximum likelihood, right? Okay, let's get into the loop. Now, what I'm going to do from now on, I'm going to show this notation for ELBO. So ELBO is a function of the W. These are the weights that are modeling Q distribution that we need for sampling. Theta, which is the parameters of my generator, and it depends on the particular point x, right? The point that I have in my data set, right? The data sample, right? So it depends on all of them, so I'm going to show it in this form. And what I want to do, I want to just use this ELBO to compute the log likelihood, right? And why do I need that log likelihood? Because then I need to just sum up the log likelihoods to do the maximum likelihood estimation. So this is the final purpose that I have. I want to maximize log likelihood, right? And this means that this is the exact expression we had before. So I'm going to average it over the data samples that I have, the log of the marginal distribution. But now, instead of the log of the sample likelihood, I'm going to replace the evidence lower bound, right? So I'm going to replace this guy with this term. Everybody's cool? So log of the likelihood, sample likelihood at the point x is going to be the maximum of the evidence lower bound computed for that particular point. Everybody's clear? As you understand, as compared to the previous topics, it's a bit more complicated, but we are going gradually towards the complicated thing. So it's totally normal. If it's a bit confusing, you can always ask, right? Mathematically, it's clear, but when you want to just think about it in a high-dimensional way, it's a bit like too much. I do understand. So everybody's cool? Great. So right now, I've done nothing specific. I just replaced this log with the maximum of evidence lower bound. And if I want to just solve this problem, if I want to maximize it over theta, this term, right? So it's good that we think about it algorithmically. So if you think from algorithmic point of view, you're going to start understand what is happening here in terms of the computation or in the level of complexity that we are dealing with, okay? So let's look at it together. So say I want to compute this log term, right, for one particular theta. And then if I'm able to compute this log likelihood term for one theta, then I can just put it inside one gradient descent loop to maximize it, right? So I just want to compute the log likelihood right now, okay? Now, if I want to do that, what I'm going to do, I'm going to sample a batch of data samples, right? Multiple x's that I can use to average. Now, for every single sample, I need to just compute this term inside the brackets, right? So it means that I need to find the maximum evidence lower bound, right? So if I want to do that, I should go ahead and first compute evidence lower bound, right? But if you look at the term here, the evidence lower bound, it's given in what form? It's an expectation on the latent itself, right? If I want to compute this first expectation, what should I do? I need to sample lots of z values, right? Z samples, and then I average this term log of model likelihood for all of them, right? So this is what I'm going to do. So for every single point that I have, I'm going to sample, say, R different samples. Okay? R different samples of latent, right? So I have my Q. My Q is fixed right now, right? Q of W is fixed, right? Now, Q is fixed. I'm going to sample R different samples from it, right? Now that I have lots of samples of Q, I am able to compute ELBO over this latent batch, right? So for every single point, when I get into the loop, I am going to sample some latents, right? And using those samples, I'm going to compute that evidence lower bound, right? Everybody's clear? Now that I have this evidence lower bound, what should I do to that? Look at this term. What should I do? Before I come out of the loop, what should I do? I need to maximize it, right? If you want to maximize such a function, what do? You're going to use gradient descent again, right? Or gradient ascent, right? So again, you're going to use a gradient-based algorithm, correct? So it means that I am going inside one gradient-based algorithm, and I start just iterating, right? So for every single iteration, I need to repeat everything above as before, right? So I'm going to have multiple iterations till this ELBO is getting to its maximum. Now that I get it close to the maximum, I'm going to save it as one of the ELBO samples, right? Then I go for the next data point, and so on. Every single data point, I need to maximize ELBO, right? And then I take that ELBO as the sample ELBO, right? And now that I have everything done, I'm going to average it over the samples that I had on my data set. Everybody's clear? Questions? So moral of the story, if I want to just go ahead with the basic form of ELBO, the thing that I need to do, I need to just do one loop, one extra loop of optimization inside my log likelihood computation, right? Now, when I want to maximize the log likelihood, every single time I need to call this loop, right? Because when I maximize log likelihood, essentially I'm going to use again a gradient descent or gradient ascent, right? And every single time that I'm computing the gradient, I'm going to call this guy, right? So there is one optimization loop for W inside the optimization loop for theta, right? So this is essentially a two-tier optimization loop, right? And then the complexity is going to just scale up with order 2, right? Quadratic now, right? Which is eventually as complex as using Hessian matrix, right? Because in Hessian matrix computation, you're again computing second order derivatives, right? For every derivative, you are going to compute a bunch of derivatives, right? And this is the same amount of complexity. From deep learning, all of you know that this is a complex thing to do, right? So we are not interested in second order algorithms at all. So this guy is a second order algorithm. We don't like it. Everybody got the issue? What is the problem? The problem is essentially the fact that this maximum is inside the expectation, right? And if I want to maximize, if I want to correctly compute my log likelihood, I essentially need to maximize the ELBO for every single sample. This is what variational inference tells me, right? Everybody's cool? Questions? Now, okay, great. So this is computationally expensive. I'm not interested in doing that. What do I do? Well, this is machine learning. We always come up with approximations, right? So the idea here is that if I use Jensen inequality, it's easy to say that expectation of the maximum of a function is larger than or equal by the maximum of the expectation of the function, right? If you have, forget about the Jensen right now, if you have two functions and say these functions look like this. One of them is this function, the other one is this, right? Now, if I add them up, right, maximum of this guy is here, maximum of this guy is here. If I add them up, When these 2 points are exactly on each other, then the maximum of the sum is exactly sum of maximums, right? But when they are not on the same point, right, the maximum of the sum is definitely smaller than sum of maximums, right? So when you have multiple functions and you add them up, so the maximum that you see on those in this addition is definitely less than the maximum that the thing that you get when you add up all the maximums, right? So here in the left-hand side, I am just doing the maximum of everybody here, right? Whereas I'm adding up all the maximums, whereas here I am finding the maximum of the sum, right? And definitely this right-hand side is smaller, right? If I am lucky, it's going to be exactly the same. If I'm not lucky, it's going to be smaller, right? So what I can say, okay, I'm maximizing the likelihood over my generator, and then maximizing it is essentially means that I should maximize this term. But then I can take this maximum out of the expectation and just write a lower bound, right? So I could say that I maximize it on both theta and w together at the same time. And the expression that I am maximizing is the average ELBO. Everybody's clear? Everybody's cool? So what about this guy? Is it again an order 2 optimization problem? No, right? Because that term on the right-hand side, the objective that I am maximizing, is something that is average of lots of computations, right? So this is like empirical risk that we always have, and then we are doing maximization on all the parameters inside this term, right? This is an order 1 optimization problem, right? And I can simply do it by gradient descent, right? This guy is better than the other one in terms of computation, but the fact is that this is not exact, right? Now, what do? Okay, we are limited in computation, so we always hope for the best, right? So we're going to say, okay, we hope that this bound is tight. Even if it's not tight, we hope that it's going to give us good gradients. And we simply assume that maximizing the log likelihood is essentially equivalent to maximize the expected ELBO. Everybody's clear? So I do not accept it from you if I hear one day in my life that any of you say that maximum likelihood is exactly maximizing average expected ELBO, because this is not. Look at the first term, right? So maximizing likelihood is maximizing the expectation of the maximum ELBO, right? Clear? When you maximize the expected ELBO, then you are doing approximation. You are essentially computing a lower bound. This is not accurate maximum likelihood anymore. The reason that we do it is because of computation, right? We don't want to have two tier. We don't want to have an optimization inside an optimization, because this is going to be super complex. Everybody's clear? Questions? No question? Okay, great. So we can now write down the algorithm like this. So if I want to compute the log likelihood, but this time I do not compute it exactly, I just compute it approximately, I'm going to get my batch of samples. Then when I get into the loop for every single sample, eventually I do all the computation at once, right? I'm going to do sample a bunch of latent, use those latent to compute evidence lower bound, and then I'm going to take that computation to be one sample evidence lower bound, right? Now that I have this guy, I'm going to just, average over all the batch of data that I have. This is going to be my log likelihood or estimate of the log likelihood. And then, of course, I give this guy to a gradient-based algorithm to optimize, right? And that one is something that I can do. Everybody's cool? Question on that? Okay, great. So moral of the story, this is, in general, we are always going to look at the whole, ELBO maximization problem as a kind of, in an approximative form, in a kind of a single loop of optimization. Now we can simply say that maximizing the log likelihood is eventually equivalent to minimize the minus evidence lower bound, right? When it's averaged over the whole data samples that I have, right? So this is going to be the target that we're going to pursue for training our model from now on, right? But you do know that this is not a very accurate one. This is an approximate one, right? Great. Cool. Now, eventually, you have theoretically whatever you need to understand how variational autoencoder works. So this is the time where we start to just develop the variational autoencoder architecture. So nothing is specific. The only thing that we need to add to all of these discussions here is that, first of all, how do we model this Q term, right? So we talked about this, that we need to have a model for Q, right? The distribution which we use to sample latent from, right? This is going to be our encoder. We're going to see it quickly. First of all, how we can model this guy, this is the first thing that we need to know. And the other thing that you need to know is that, well, if you just use those Gaussian models, how exactly that evidence lower bound and the training loop going to look like, right? So this is the only thing left that we're going to do. Now, the first thing about this guy, how we can model it, I mean, eventually this guy needs to be a probability distribution, right? And the probability distribution should be on what guy? What is the guy who is random variable in this expression? Z or X? Q is a distribution on Z, on the latent, right? For a given X, right? So it's supposed to get one sample X, one data sample, and then it gives you one distribution on the latent, right? So you think about it, you start to build some intuition. X is one data sample. It's going to tell you where in the latent space this guy could be represented, right? That is the distribution, right, of Z. This is the first thing. And now, what kind of property this guy needs to have? If you remember, this Q was supposed to somehow model or approximate the posterior distribution of Z, right? If you replace Q to be the posterior distribution of Z, it's P of Z given X, right? When you marginalize it over X, what's going to happen? If you multiply it with Px and you integrate it over Px, what's going to happen? It should be latent distribution, right? So whatever distribution you are proposing for Q, it should have this property that if you marginalize it over Q, it could end up with the latent distribution. If you have one model which is not able to do that, then obviously that model is wrong, right? So it's not simply modeling the distribution. It needs to be a distribution plus being able to marginalize into the latent distribution. This is one thing that we have extra to a normal modeling of distribution. The other thing is that, say that we model this Q. Now the question is that when we want to optimize, evidence lower bound, as we discussed in the other slide, we need to compute these gradients, right? And if you look at those, I'm going to open it up for you. If you look at those expressions, some of these parameters are showing up in the distribution by which you are doing the expectation, right? And this is not a kind of very classic gradient that you use to compute, right? How we can exactly compute such gradients, we are going to discuss that. So these are the two major things that we are going to discuss. So basically, you are going to use the trivial backpropagation plus one tiny bit of trick to be able to do that, okay? But we're going to discuss it. Now,